Hello everyone, welcome to 1045 Engineering. We are here with yet another video in our Grind 75, a Better Blind 75 coding series. So today's problem is on binary tree right side view. So we are given a binary tree like this 1, 2, 3, 4, 5, and we have to print the right side view of this. So it's just like what if you are viewing this binary tree from the right side as suggested by the arrows. Then these output should be 1, 3 and 4 because from the right end you can only see these nodes, right? So let's quickly jump into the problem statement, understand it and start solving. Last time we have solved the subset problem, we'll mark it checked. You can find it in the list. Let's start with binary tree right side view. Okay, let's go through the question. Given the root of a binary tree, imagine yourself standing on the right side of it. Written the values of the nodes you can see ordered from the top to bottom. Okay, so we have to print in this case 1, 3, 4, right? Let's say 5 had one child node, 6 on the bottom. Okay, then the output should have been 1, 3, 4, and then from right side we can see 6 directly, right? So please take a minute. It's very easy to understand the problem. Please take a minute and think of a solution approach. Ready? Okay. How we are going to achieve this is we'll take the most intuitive and simplest approach. We can go with the level order traversal, right? Level by level we go through it and we print the rightmost node. How will we print the rightmost node? If we go through level by level and we have all the nodes on the current level, let's say 2 and 3, we'll start iteration, and once our iterating pointer, that is I, has reached the size of that current level, we can print the rightmost node, right? Let's go through the code and you'll understand it much better. It's a very simple problem statement. Okay, let's start. So what do we need? We need the result. So we can say list integer result is equal to new array list. Okay, then the base case, if root is equal to null, we'll simply return blank result, right? Let's just comment as well, base case. Okay, now next we need to do the level order traversal. Now how do we generally do the level order traversal? For all the level order traversal we follow the approach that we can directly consume the nodes in the queue. Okay, let's start with that. So we'll say use a queue for level order traversal. So we'll make a queue of integer q is equal to new linked list, right? Okay, then we'll add the root node, that is 1. So q dot offer root. Okay, now we'll check for until the queue is empty and we'll keep adding the child node, right? So we'll say check while queue is empty, while queue is not empty. Okay, we'll check int level size. Okay, so level size will be queue size dot size. Okay, so let's do a dry run in parallel. So right now in our queue we have only one node, that is 1, so the size is also 1. Okay, this is also 1. Then we'll start traversing for each level. So you can say traverse each level and add the rightmost node to the result list. Okay, so we say for int I is equal to 0, I is less than level size, S is capital, size I plus. Okay, we can say tree node. Why tree node? Because this class is tree node. So all the nodes are of type tree node. You can see here, right? So tree node current is equal to QE dot poll, right? So our current in this case would be 1, and since we polled it out of Q, Q will be blank, right? Now we'll check for 1. We'll check if I is equal to level size minus 1. Okay, we'll say rightmost child check, not so good, check for rightmost child, right? Child node. Okay, so we are checking if I is equal to level size minus 1, then level size is 1, I is equal to 0, so 0 is equal to 0, so we can print this. So we know that we are at the rightmost, right? Current is the rightmost, so we can say result dot add current dot value. Okay, now we'll check if, since now we want to add the child node for this current node into the queue, so we'll check for the left and the right. So let's comment check for left child. Okay, so we'll say if current dot left is not equal to null, then q dot offer current dot left, right? So since current dot left is not equal to null, which is 2, it will get added to the queue, so we have 2 added to the queue. Similarly, we'll check for right, check for right child. This is chill. Check for right child. If current dot right is not equal to null, we can say QUE dot offer current dot right, and that's added. So since its right is not null, 3 will get added to the queue. We are entering from this side, so 3 will get added here. Okay, this is the front, this is the back. Okay, now 3 has been added to the queue. Okay, now what will happen? Okay, let's whenever we are done with the while loop, we'll return our result. So we can say return result, but let's finish our dry run. Now 3 has been added to the queue, 2 has been added to the queue. We are done with these loops. We go back, our for loop is done because a value of level size was 1, right? Where do we have the level size? Oh, we have written it directly as size, right? You can say level size. Level size is coming directly from the queue size. Now so let's keep it level size or size. Okay, now since now in our queue we have 2 elements, 3 and 2, so while queue is empty, no, queue is not empty. Level size is equal to q dot size, so level size, which was earlier 1, has now become 2. Okay, now we'll check I equal to 0, I is less than level size. Okay, tree node current is equal to q dot poll, so 2 will get removed from here and it will come as the current node 2. Okay, since in the queue we enter from one end, remove from the other end. It's FIFO, first in first out. Okay, so current is now pointing towards node 2. We'll check if I is equal to level size minus 1. Value of I is 0, level size is 2, 2 minus 1 is 1, so this loop is not true. So 2 will not get added to the queue. Does 2 have a left child? No, 2 does not have a left child. Does 2 have a right child? Yes, 2 has a right child, so that will get added. So 5 gets added here. Okay, but in a result list as of now, what has been added into a result? 1 has been added as of now. Okay, next we'll check. I will move forward, I plus plus, current is equal to q dot poll, so 3 will get removed and 3 will become our current. Okay, now we'll check if I equal to level size minus 1, 1 is equal to 2 minus 1, 1, so this loop is true. So result dot add current dot value is 3. So 3 gets added to the result list. Then we check if 3 has a left child. No. 3 has a right child. Yes. That gets added to the queue. So to the queue, now we have added 4. Okay. Now this for loop is done. Since I was less than level size was only 2, we'll move forward. Is queue empty? No. Level size equal to queue dot size. What is the new queue size? That is 2, right? So queue size will get updated from 2 again to 2. We'll check for the first element, I equal to 0, current is equal to queue dot poll. So 5 will get removed. 5 will be our current. We'll check if 5 is equal to I equal to level size minus 1. 2 minus 1 is 1, I is 0. So no, this will not loop not get executed, and 5 will not be added to the result. 5 has any left child? No. Right child? No. Okay. So for loop moves forward. I plus plus tree node current is equal to queue dot poll. In queue right now there is only 4. So 4 gets removed, 4 gets added to the current. I equal to level size minus 1. Level size is 2. 2 minus 1, 1. And I is equal to 1. So this is true. Result dot add current dot value. Current value is 4. So 4 gets added to our list, right? And then current node, which is 4. Any left child? No. Any right child? No. Sorry. So this is over. Now, what is the queue size? Queue size is blank. So this while loop gets completed, and in the end we return the result. Okay, that is the simplest approach and the most intuitive one. We have some typos again. What did we do wrong? Q dot offer root. What's the name? Q is correct. QUEUE. Tree node cannot be converted to integer. Oh, why? Oh, okay. I have created this of integer type. We'll make tree node. Okay, simple enough. Okay, let's see. Cool. Let's submit. Okay, beat 69.77. That means there might be approaches better than this one. You are welcome to try them out as well, or if you are aware of some, please let me know in the comment section. I'll be happy to try them out. This is the one of the most simplest and the most intuitive one. Okay, and since we are traversing each node only once, overall time complexity is over fine. Okay, so yeah, that's all from today's video, everyone. For anything, please let me know in the comment section, and in the end, please like, share and subscribe. Thank you.